Hello everyone! In the last couple of videos we have looked at linear functions. In this one we are going to look at the other function in this chapter, the exponential functions. First I will give a bit of a reminder about what exponential functions are, and then we are going to look at growth vectors, first for several units of time and then for half a unit of time. Just like with the video on linear functions, there is no new explanation here. We have all seen this before about exponential formulas, so it will mainly be a reminder and I will try to go over it rather quickly. If you want to get some more detail, you will have to have a look at my earlier videos on exponential formulas. Alright, so let's first remind ourselves about exponential functions. Here you can see two graphs, both of exponential functions. And an exponential function, a function for an exponential relation, is a function where every step we multiply by the same number. This means that it either rises very fast, like the graph of function f does, or it will get closer and closer to zero, like the graph of function g does. Now the function for this looks like so: fx equals b times g to the power of t. And because we usually talk about amounts with exponential functions, it may be about a deer population or about money in your bank account, that sort of thing. We don't talk about the y-intercept, we instead talk about the initial amount, and that is the b in our function. And then the number that we multiply by every time, we call that the growth vector, and we use the letter g for that in our function. Now you don't have to be able to get the function from the graph, but as an example, the function for graph f here would be given by 5 times 2 to the power of t, because it starts at 5 and it doubles every step of the way. So that's just a reminder about what an exponential function is. Let's have a look at the growth vector. And we're going to start with the growth vector for several units of time, for a larger unit of time. Using the example from before, let's again assume that the growth vector is 2 per step, 2 per hour. And suppose you want to know what happens per 3 hours. Now for 3 hours we multiply by 2 and again by 2 and again by 2. So we multiply by 2 to the power of 3, or by 8, meaning that per 3 hours our growth vector is 8. More generally, if we go x hours ahead, we multiply by 2 and by 2 and by 2 and by 2, x times in total, giving us 2 to the power of x, meaning that our growth vector per x hours is going to be 2 to the power of x. Now this is all with the example where the growth vector was 2 per hour, but it works the same way with different numbers. If our growth vector is 5 per hour instead, then the growth vector per x hours would be 5 to the power of x, etc. So that is the example for a larger unit of time. Let's also remind ourselves what happens for half a unit of time. So we're still going to use the example of the growth vector being 2 per hour. But now we want to know what happens per half an hour. So let's make a little table for that. We know that if we go 1 step ahead in time, 1 hour ahead, the amount doubles, in this case from 1 to 2. And the question then is, what kind of step do we take per half an hour? What can we multiply by and then multiply by again to get from 1 to 2. Now I'm not going to fully explain this. If you really want to go deeper into this, you can watch my video more on growth vectors. But it turns out that the step we're going to be taking is square root of 2. And more generally, no matter what the growth vector per hour is, the growth vector per half an hour, for half the unit of time, is going to be the square root of the growth vector. So that is the thing you can remember there. That's all I have to say about exponential functions for this video. I hope you've been able to refresh your memory on what exponential functions were and what the growth factor did if you changed the unit of time.